To make sure this strategy is going to do what we want, let's step back and look at it more generally and abstractly. H is a hash function, and in general, a hash function maps some arbitrarily large value, it could be a string or some data structure, into a fixed size number. And you've certainly seen this for data structures. When you have some values that you need to reference by their keys, you can create a hash table which involves hashing those keys. In that case, you expect your hash function to sometimes give you collisions, especially if you consider the hash to be the result of the hash function modulo the size of the table. Those kinds of collisions are inevitable. And by collisions, we mean that you have some key x and some key y that are not the same, but they have the same hash. So in the context of a hash table, this means after you hash the key, you need to double check that what you find at that point in the table is the key you expect. And if not, do something else. Perhaps you have a linked list there. Perhaps you do double hashing or something like that. But the point here is that these hash functions, because you're going to end up with collisions on the slots of the table, you don't care too much if two values or keys in the sense of the hash table can be constructed that have the same hash code. You want them to be different usually for the algorithm to work, but you don't care if it is possible to go backwards and construct something that creates collisions, as long as those are relatively rare. In the cryptographic context, though, we're doing the same thing. We're using a hash function to map an arbitrarily large message into some fixed size summary of that message. And we use that as a proxy for the overall value, not a way to find something mapped from that value. So we want something that reliably represents the original value. That is, we don't want collisions ever. Because if you can create a collision, then Mallory can construct a message where something is changed, but the end result still has the same hash result as the original message. And so it looks like it was the original message as intended. So by impossible, we mean if I've got values x and y that correspond to these messages. If hashing x gives me the same thing as hashing y, then we want that to mean that x is definitely the same as y. Now, while that may be what we want, you don't have to think long about this to realize it's just not possible to make collisions impossible. We are mapping an arbitrarily large value into some fixed size number, and that size is smaller than the original value, so just by the pigeonhole principle, it must be that some of the large values map to the same number. Fortunately, in a cryptographic context, we can make those collisions infeasible to find if you go looking for them. What we have to do is pick a big enough number so that even though there are many collisions in principle from all the messages you may send, there's only so much time in the universe to send so many different messages, so you only hash to so many of those fixed size numbers. And if there are a lot of them, that's still too many to try. So that's going to be our strategy. We want a hash function that's good enough and with a big enough target that no one can find the collisions. No one will hit them in practice. No one can find them even if they try.